Okay, so last class we basically just discussed what registers are. So registers in MIPS are stored bits of information that in a way that they can all be read from or written to simultaneously. And here we talked about RS and RT, so we have two source operands, but we only have one register, right? So let's say I want to do something like B equals A plus A. Let's say that's the compiled code. So what I would do is I would have RD would be the register where I store B, and then RS is where I store the first A, and then RT is going to be the second A. So this is the instruction, right? So they're both going to try to access the same register simultaneously, right? So what the register is going to do is it's going to have the ability to do something called dual read, single write, meaning that it can be read to twice in the same cycle, meaning that if we need two copies of it, you can get that simultaneously have both of those be the input to the arithmetic logic unit, but only write once. You don't want it to be able to write twice. That's something called cache consistency, which we'll learn about later in the course when we get to memory. But the idea is that you want to make sure that the value at any given moment is the exact value it should be. And so these function types, opcode was the 6-bit value indicating the type of instruction. RS and RT are your source operands. RD is your destination operand. Shift amount for shift left logical, shift right logical. That'll tell you precisely how much is you should. It's 5 bits because you can shift up to 32. So it's a binary representation. So if you in your grade code, if you were to do this, you would take a in MIPS, you would take a 5 to 32-bit decoder to select which one you want to do for a one-hot encoding. For your data path, you're still going to have a 32-bit instruction, but you're only going to be able to have up to 8 here. So you're going to have a 3 to 8 decoder, at which point that you can use that, which will tie into the last problem on your assignment, which the last two problems are just shift left and shift right logical based on one-hot encoding. So that's how you're going to do that. So you have the 3 to 8 decoder already done. You're going to have the shift left logical. You're going to put that in your ALU, which most of you have already done. You already have the multiplexers that you'll use to control that. So you can see how these pieces are starting to be put together so that you can start to build the architecture. And then the function is selects specific variant on the opcode. The opcode for all R-type instructions is 0. I kind of discussed. Did I discuss this with you last class, or? Okay, I'll quickly go over it again. So registers take two values, RS and RT, add them, goes into the destination register. So registers used for instructions to perform an operation on two register values and places it in the result in a register. Used for data transfer instructions, we talked about branch instructions and I-type instructions. And jump to a new address. So this is when we get to a end of a function or the end of a loop and we want to go back to the beginning of the loop or go back to main, we would use jump instructions. And so to clarify, because you're going to see this as RS and RT here, oftentimes for branch instructions, you'll be comparing these two values. In I-type instructions, you'll have, if it's B equals A plus 5, for example, A would be in RS and B would be in RT. So this would serve kind of as the destination register. And in your jump address, we're going to be, in section 5, we're going to learn how to take a 26-bit address and turn that into a 32-bit address. Okay. So, and this is where we left last class, right? Okay, so the register names, and discuss that there are certain ones. These are function arguments, temporary registers, which you'll be using these a lot in order to be able to keep track of pointers, temporary values. Because if you have multiple, let's say if I'm adding B equals A plus C plus D, you don't want to store that value in B because you only can add two registers at once. So but the coder at no point asks for the result b equals a plus c. So if you update that first, you have an entire cycle where the value of b is incorrect, because that's not what the coder asked for. And we're going to be going into examples of that later. So what you do is you use a temporary register to store that register, add the third register, and then store that into the destination result. And then global pointer, stack pointer, and frame pointer are used for determining where the function is in memory. The OS kernel, we're going to be going into exceptions in section 6, but these are this is what happens. You use these two registers to store what type of exception you have and where the instruction took place. So remember, if you know, you go into you have the blue screen of death in Windows, right? And you see these two giant X values. That's what's stored. So basically, it's using those two giant hex values to indicate, here's the problem, here's the instruction it occurred at. So that way they can troubleshoot the problem. And if it made it all the way up to the blue screen of death, for those of you who have coded in Java and familiar with try-catch blocks, and just throw it up and throw it up and throw it up, so it hit the highest try-catch block without hitting any other exceptions, so it shuts down the computer. So this is okay. So this is where I kind of end. I ended with this discussion of what register transfer instructions are. Register transfer instructions describe what's going on inside the registers and where the result's going to be. Right? Let me scroll up here for a minute. So if you look on Blackboard and you look under the MIPS screen sheet, you're going to have this entire list of every single instruction that MIPS does. And on the exam, you'll be provided with a copy of the MIPS screen sheet. Now the idea is to compare here RS, RT, and RD, right? RS, RT, signed immediate, and then jump address, right? So here, this register transfer instruction language right here is the operation. It's telling me I'm going to take the two values here, and then I'm going to generate, using the opcode of the function, the value from the ALU control that's going to go to the ALU and say, add these two numbers. Add those, and then store them in an additional register. So that's what this means. And specifically, it's described as an R-type format. Now, the opcode is the first 6 bits, so that's just 0. All R-type instructions are going to have an opcode of 0 in MIPS. And the way you differentiate them, for example, the way you differentiate addition and subtraction, is by using the last 6 bits of the instruction function. In this case, it's 1 0 and then 4 zeros. That's what 2 0 hex is in binary. So the MIPS instruction registers I've indicated 5 bits, and they are used to select one of these 32 registers here. And so I kind of alluded to this problem. How would these values be translated in order to select the following registers we need? What if an RS and RT are the same register? What did I just say? What's the capability of the register that describes what would happen here? F equals A plus A. What's it? Dual read. Dual read, and then dual read, single write. Exactly correct. And of course, that's because the first sentence here, it says in order to do this, registers need to be dual read, single write SRAM. So basically, what this paragraph here is talking about is you use control signals that are generated by the controller. The controller is getting a value from the opcode, and it's going to generate 9 control signals. It's going to generate a value register write to indicate whether or not you want to write to the register. It's going to develop one called register destination that's going to choose between RS and RT. So in order to differentiate whether it's an R-type instruction or an I-type instruction, it's going to create a 2-bit ALU op that's going to go to the ALU control unit that's going to be combined with your function in order to produce those control signals that we did previously in section 3. If you recall, when you're developing your ALU and there are these control signals that are driving your multiplexer, it's generated by developing that control signal from the ALU op plus the values in the function to develop your signals that go to the ALU. I'll get to your question in a second. Additionally, you have to have, we're going to have something called data memory, which is your non-volatile long-term memory. And every instruction is going to have a memory read or memory write. Since we are only writing to registers here, and we're not reading from the memory or writing to the memory, we're going to have memory and memwrite be 0, because we're only reading from local fast registers as opposed to the slower non-volatile memory. And we're going to have something called memory to register. We're going to be talking about load and store operations from this data memory, and that's called memory to register, at which point it's going to determine whether or not, for example, let's say I get something that's put out from data memory, and I have this operation. Well, I want this value. I want the operation result from the ALU, not the data memory, right? So what's going to happen is I need to make a decision. Because we'll get into load words. Load words actually make arithmetic calculations to determine where the memory is. So you have an added value and a value from data memory, and so you need to select between them. And that value is called memory to register. So if it's 1, that means we want the, I'm probably going into too much detail into what's going on in section 6. But if it's 1, then you send this value from data memory. If it's 0, it's going to be an R-type instruction where we get the value from the ALU. So, as I said before, I'll provide a copy of the MIPS screen sheet. So let's go into a basic, so this is kind of a basic description of how this works. So we have a translate the following C code into MIPS register transfer language, then MIPS assembly language, then MIPS machine code. So we're going to go from, we have some basic C code here. It's A equals B plus C plus D, a very simple C instruction. And then we're going to say, here's the representation on the MIPS screen sheet. Here's the representation in the assembly language. And here's the representation in machine code. And so this is the process of what happens when you run, I mean, this is a very basic process of what happens if you run a compiler. I don't think we want to get into lambda calculus today or ever. Some of you want to run from that. I've seen Turing Award winners shudder at the mention of lambda calculus. But we're going to see this. So the first thing is, for recall, we only have 2 registers that we can operate on any given moment, right? So we have to have, and you have to, the order of operations is important. You have to do what the coder tells you to do in this case. You're not guaranteed to get efficient code. So first thing we're going to do is we're going to look at B plus C. And so these 2 values right here, I have the assembly language on the left and the corresponding register transfer language on the right. So if you're doing 2 additions, B plus C, you look at your MIPS screen sheet, RS equals, this is S1, meaning S1 is B. This is S2, which means it's C. So we're adding B plus C here, and then this is $T0. From your homework, do you remember what T0 is? Temporary register, exactly right. So the reason why we do that instead of putting in an A is because we have an entire cycle where the value of A equals just B plus C, and that's not what we asked for, and that should never be the case. So then the second instruction becomes taking this T0 here and adding S6. Now S6 is D, as stated in the problem. So now we have T0 plus X S6. T0 is the sum of B plus C, so now we have B plus C plus D, and stored into S0, which is A. So now we have our register transfer language, and we have our assembly language. So now the next step is translating this into actual binary values. This is what's physically going on when you press compile and then it runs your program. So we have I've broken it up into, we have 2 R-type instructions. If you look at the MIPS screen sheet, if you recall from earlier, we have the opcode is 0, meaning it's 6 zeros, right? And the function is 20 hex. That means it's 1 0 and then 4 zeros, because it's also going to be 6 bits. And the shift amount is going to be 0 because we don't shift, right? And so here I have function equals 20 hex. So the first instruction Also available on the MIPS screen sheet is this. This is on their MIPS screen sheet, right? So here's what this means. We have S0 through S7, right? And it has number 16 through 23. And we have a 5-bit value for each register to indicate what this means. So this 16, S0, means that the value in the register, the 5-bit register, is going to be what? Bingo, 10000. If I have S1, that means it's, if S0 is 16, what is S1 going to be? 17. So what is the value in the register going to be? 10001, right? All the way up through S7, which goes up to 23, and so forth. Temporary registers, 8 through 15. So if you have, we had T0 in our solution, right? So T0 is 8. So what's the binary value going to be there?
1000 or 10.
Yeah, 0, 1, 0, 0, 0. Yeah. Remember, it's going to be 5 bits. So going back to our solution, we now take from the MIPS screen sheet our opcode to 0, our function, which is 20 hex. We know that S0 is 16, S1 is 17, S2 is 18, S3 is 19, and S6 is 24. Should be 22. I'll fix that. And T0 equals 8. So for the first instruction, we're going to be adding S1 and S2 and storing it into T0. Let me scroll up here for the people in the back. So the first instruction is add. You have opcode is 0. RS, this value, is equivalent to this one. I know this is where students get confused, so I want to be very clear about this. The first register in the R-type instruction matches the second register here in the assembly language instruction. And if you recall from earlier in the semester, I saw a couple of people go, if you recall earlier in the semester in Chapter 1 Topical Guide Objectives, I talked about how Patterson said that the MIPS is based on performance and they make compromises in other places. This is one of them. So S2 is 18, and it's here. That's this one. RD, we're using a temporary register, so that becomes T0. Shift amount 0, function is 10. If you split them up, that's 20 hex, right? And then second addition instruction, 000. RS is going to be your first addition, so that's T0, so that's 8. So that's this one, correct? S6 is going to be 22, so let's fix that. I have 16, 8, we're not going to 8. I have to add 4, which is 20. So I had 22 correct there, I just made a typo here. So it's 22. RD is going to be 16 because S0 is in 16, and that's where ultimately we're going to store the value, and that matches this one. Shift amount is 0, and function is 0. So before we move on, does anybody have any questions about what I just did? Yes?
Your function value, is that always going to be 20 hex, or is it dependent on what you're doing?
That's a very good question. It's dependent on what you're doing. The R-type instructions are always going to be 0. And the way you differentiate, for example, subtraction is an R-type instruction, but it's going to have the same opcode. The difference is the function is going to be different for subtraction. And we happen to have internet here, so would this be a miracle? Probably not.
Yeah, just a little internet.
Where is it? Content, topical guide objectives. Oh, reference files. You go under reference files, and then MIPS screen sheet. You'll have the first page of this on your exam.
Fill out? Or
No. You will have it as a reference. Yeah, good luck filling this out. I couldn't do the whole thing myself. So here you have, I'll get to your question in a second, Josh. So you have add and you have function. So if we go down to subtract here, it's going to be RS minus RT equals RD. I'll scroll up for those of you in the back. And it's 0 and 22 hex.
That's 0, is that the...
Opcode. So for the format here, it's opcode / function. So for these values here, you see how there's only one number? Those are going to be I-type or J-type instructions. Because if we go back here, see how there's no function value for I-type? Yeah, Josh, what's your question?
So why is the 20 hex 1000?
Okay, so this is binary to hex conversion, right? So hex is basically the same thing as 4 bits of binary, right? So if you have binary goes from 0 to 1, and hex goes from 0 to 9, it needs to count 16, right? So it goes from 0 to 9, and then we run out of numbers because we only have those. So then we start going to A, B, C, D, E, and F, right? So F is 15, C is 14, D is 13, and so forth. So if you have 20 hex, and it's a 6-bit value, this means these 4 bits are going to be 0, 0, 0, 0. That's the least significant bits. And this is going to be the 2 most significant bits. So this would be 1, 0. So if I had, perfect example, let's go to jump instructions. 2 hex. It just says 2 hex. It doesn't even say 20 hex. What do you think that means in binary? 0, 0, 1, 0. But this is only 4 bits, right? My opcode is having, I put 2 on the front there. So the jump opcode becomes 0, 0, 0, 0, 1, 0. It has to be 6 bits. Okay? Did that answer your question? Any other questions? Yes. I'm sorry, George and then Adam. Yeah.
When do you use the shift amount?
Okay, we'll go into that. Well, that's a very good question. We'll cover that a lot today. Adam.
So what would you do if you had like 236 hex? Would it then be 4 zeros, 4 zeros?
Oh, you mean like? Oh, well, this is outside the scope of the instructions. If you're doing 236, then you just split it up like this, and you would just go 0, 1, 1, 0, and this becomes 0, 0, 1, 1, and 2 becomes 0, 0, 1, 0.
So they don't get more than...
Yeah, well, no, if you had 236 hex, you'd have a serious problem because that means your opcode is longer than 6 bits.
Right.
So, but I mean, this is how do you translate from binary to hexadecimal. So 24 hex here for load byte unsigned, which we won't cover in this course. But let me find a and. You guys have and in your ALU, right? 0, 24 hex. So what's the opcode going to be? It's an R-type instruction. So what's the opcode going to be? For 6 bits? All zeros, exactly. How many zeros? 6. 24 hex. What's that going to be for your function? 1, 0, 0, 0, 1, 0. Exactly right. 0, 1, 0, 0, 0, 1, 0. Right. Okay, any other questions? Adam, I answer your question. And it's 1, 0, 0, 1, 0, 0. Yeah. If dyslexic not a my Yoda, you must. Okay, so let's look at, as I include here, this is why I included that topical guide objective and say over and over again that MIPS is a compiler-driven encoding in the micro engine. You have to do what the coder says. So example 4.9 is a good example of this. So we have the same thing. We have G's in S0, H's in S1, I is in S2, J is in S3, F is in S4, right? And the C code is F equals parentheses G plus H end parentheses minus parentheses I plus J end parentheses semicolon. So, without looking at the screen, what do you think we'd have to do? If you were doing this in 6th grade or whenever you took algebra, what would you have to do first?
And then I and J.
Exactly right. You'd have to add G and H, you would add I and J, and then you would subtract them. So if you were doing this in MIPS, what would you do? Add G and H and do what with it? Store in a temporary register. Very good. Minus, then what?
Add I and J.
Add I and J, store in a temporary register, and then you take those two temporary register results and
Put it in the same.
store it. Exactly right. Very good.
Is this like the tree thing?
Yeah. Sort of. I mean, the compiler does a lot of this work for you. I mean, you're learning basics of how compilers work. Like very, 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 very basic. I'm having flashbacks to compilers class in grad school. It's a funny story about my compilers class, real quick. So if you think that I put you through too much work, on the syllabus, he actually wrote, course outline, he put spring break, and then put break in quotes. The spring break, and then said, I expect you to be working on compilers. So if you think I'm mean, he's actually Dr. Legatti is one of the nicest human beings I've ever met, but he did do that. So anyway, getting back to this, so we've done that. You guys have actually wrote this code out. Very good. Again, these are all R-type instructions, so all of the opcodes are going to be 0. And then it's a matter of just keeping track of the functions, which I've listed out here already. Now, I have this value as red, and the reason why is because if you remember that subtraction is 22 hex, right? So just by if we're just looking at, we get rid of all this, and we were just change that into white, right? And we don't know what's going on here, and you don't know what's going on here, and you don't know what's going on here, and you don't know what's going on here, right? We can actually look at this code, this binary code, and tell exactly what's doing. So if these 3 instructions are all 0, 0, 0 for the 6 zeros for the opcode, what does that mean? Means it's an R-type instruction, right? So we correctly see that we've RS, RT, RD, shift amount, and some function values, right? So this is 16, so what does that mean? I can see some of you have it right on the tip of your tongue. Trust yourselves. Not a temporary.
That's 0.
Yes, that's 0, right? And so what is this one? If it's 17, S1. And if it's 8, what is this? So here I can tell I'm adding S0 and S1 and I'm doing something with some R-type value with S0 and S1, and it's going to be stored in a temporary register. I have a shift amount of 0, right? And so this 6-bit value, I split it up like this, then you can tell what the hex value is going to be, right? So what is this? 2. And what is this?
0.
And what is 20 hex function in MIPS? Exactly right. And y'all telling me you don't know how to code. Again, you just translate this one. Now here, what's the function value for that? 22. So what's that in MIPS? Subtract.
So, how much memory can each register store?
Each register, that's a very good question. Each register stores 32 bits. Because in MIPS it's 32 bits. And we have 32 registers and 32 bits instructions. You? I thought I saw somebody over here with a skeptical look on their face. Okay, no. All right, so common student mistakes. So here I have add sub and sub, right? So this comes out to F equals G plus H minus I minus J. Why is that an incorrect answer? They're mathematically correct. It's not. Say what you want to say. Yeah, it's not what the coder gave you, right? Let me put this all back in original color page layout, no home. Yeah, this is what. Here's what your coder gave you, right? They did it this way for some reason. That's what you have to do. And again, to hit on that, another common mistake on these types of problems is this. Add S0 and S1 stored into F. Then S4, so this becomes F equals G plus H, and then S1 equals F minus I, and then the next equals F minus J. So it's mathematically correct. So why is this specific error of what the code specified wrong? Why is that bad? Andrew.
Oh, I'm not sure about that.
Okay.
I have another question.
Okay, well, I'll get your question in a second. So why do you think that's bad? Yeah, because you have two cycles where you have the incorrect value of F stored in the register. Yeah, Andrew.
So when you talk about the coder having given us code,
yes.
Are these MIPS machines going to be designed off of a certain piece of code? I mean, do you see what I'm saying? Are these going to be building real world applications? They're going to be designed after we have a set instruction set?
Okay, so yeah, you would have the instruction set. So this is where the difference between computer architecture and computer organization comes into play. So computer architecture, system attributes to a computer which produce the logical calculations that are visible to the programmer, right? So this means MIPS is going to be designed in such a way that this code that the coder can implement in either assembly language or C or register transfer language can be then translated into these binary values and executed in the machine. So, not to go into too much, but there's this concept called Turing completeness, and MIPS is a Turing complete machine. The whole idea is that basically you can put in any what's known as Turing complete functions, and basically any computer you have is Turing complete. So it needs to be able to complete all of the operations that can be done on a Turing machine. So in order to do that, so MIPS is based on high performance execution of compiled code. So the whole idea is that we've kind of emphasized a number of times about how there's different choices for different things, whether performance or area or power consumption. Every choice the designers made for MIPS went towards performance. They didn't care too much about power. And so they wanted to make the common case Mac, they wanted it small and fast. Hence, if you remember the 4 design principles, smaller is faster. That's where that came from. So that's how that all ties into this. Any other questions? And so as I alluded to earlier in class, this is a problem known as cache coherence. So let's go to page 29. So now we're going to deal with I-type instructions. So now we have G is in S0, H is in S1, F is in S4, and we have G equals H plus 5. So for whatever reason, our coder has put brackets around H plus 5, so we have to do that first. So if we go to our MIPS screen sheet, we see the second instruction here is called add immediate. It's add I. It's an I-type instruction, so it takes RS plus the sign extended value here and adds them together and puts them in the RT register. And its opcode is 8 hex. So we go here, add I, S1 and 5. 5 is going to be in that, if you remember the I-type instruction, we have the 16-bit value. So there's going to be 13 bits and then 101. Now, I want to point something out before we go any further and answer this question. Note how, so you got subtract, subtract unsigned. There's no subtract immediate instruction. Let's scroll up. There's no subtract immediate instruction. Tying back into what I think, how I just answered your question, Andrew. Why do you think that there's no subtract immediate instruction? Combining concepts. MIPS is a compiler-driven encoding in the micro engine. Smaller is faster. High-performance execution of compiled code. Why would they decide not to do subtract immediate instruction in here?
So you can just add immediate.
You do add immediate and then do what? With that. Bingo. So the compiler gives you the 2's complement, throws it into your architecture. And that reduces the size of your controller unit. So that means your controller is going to be smaller. So we add I, we're going to add H plus 5 and store in a temporary register. And then we're going to do the R-type instruction as before, where we store S0. Now it's in this. Now why do you think I put it in this order? R equals S0 plus T0. Why is it in that order? S0 is G. And, yep, exactly right. Yes, Adam.
Why do they have a subtract function then if they could do just the add function with 2's complement?
Now, that's a very good question. Let's go to the subtract instruction. The subtract gives us RS minus RT, right? Now, RT could be anything. RT could be a value, like we could have this code. We could have, wow, I've written all over this. So we have we could have F equals A plus B, right? Right. And then we have G equals D minus F. So you have compiled code, and then you have, remember, and you remember in code you can actually enter values in real time. We cannot guarantee that the value in real time is going to be positive or negative. So therefore, we need a subtract instruction because this could be positive or it could be a 2's complement, in which case we just put in plus. But once the compiler's done and once the code's in there and it's running at the architecture level, you need to physically do subtraction. Does that make sense? So that's why, now that remember tying back in to previous concepts when you're doing your ALU and your 8-bit add sub, you have 20 hex and you have 22 hex. So you have 10, 0, 0, 0, 0, 10, 0, 0, 10. And this bit is the difference, right? Where it's 0 if it's add and 1 if subtract, right? So where do you think you're tying that bit to? Yeah, because you're add subtract, right? Your AS value, that's where it comes in, and that's why that opcode is chosen that way. That was a good question, Al. So again, this is the difference. We've already done your R-type instructions where you have opcode is 0, your function is 10, 0, 0, 0. Now, for I-type instructions, it's different. Now, on an exam, you could do this and I'll accept it, ... Because that's ridiculous to draw 13 zeros, right? So go back to the green screen, green sheet. The add immediate is 8 hex, right? We have S1 is added with 5, and we put it into T0, correct? So that's how that is done. Does anybody have any other questions on this? Because now we're about to go into branch and jump instructions. All of the people scribble. So hopefully, as we're going through this code, you're kind of seeing how all the things that we were learning so far in the course are starting to tie together, right? That all these like, why is he asking us to do this? It's starting to go, oh, hey, these things now build upon each other, and eventually. So that multiplexer ties to that control unit we were designing, and that ALU, and oh, the opcode function. Oh, hey. All right. So we're going to discuss two specific types of instructions called load word and store word instructions. Topical guide objective 4.23. Load word instructions are instructions that take an address calculated by the arithmetic logic unit and loads the value from that address into a register specified by the instruction. So we have this non-volatile data memory, and we're going to discuss what goes on in that data memory in section 5. But we have the ALU calculates a value that points to a location in the memory and says, I want this data, and I'm going to perform a number of operations on the faster registers. So improve performance by doing a lot of load operations first, performing all the operations, and then performing store operations. And the reason why is because data memory operations, so we'll cover this in section 5 in great detail, can often take up to 100 times longer than register type instructions, because oftentimes you have to go to different levels of the cache. But I'll let it throw too much at you right now. So there's this magical box with data memory, right? And in that magical box where you press the I believe button, the load word points to a specific place and says, I want these 32 bits. And we do that by calculating it with the ALU. And the way we do this is we use an I-type instruction. The register RS here, let me bring up the PowerPoint because that doesn't have corrections in terms of, this is spelling, yeah. So this sign extension immediate this is the register transfer instruction representation, and that's the 16-bit value. And then RS is what's known as the base pointer. So when you pass an element by reference, when you pass an array by reference of int star A, what that is that's pointing to the base of the array. And that's calculated, it's stored in a register. And then, so if you have A0, you just want to point at the first element, right? If you have the second element, you want to point to the next element, the third element, you want to point to the next element, and so forth. And here's the assembly language. Load word RT, which is where we're going to store it in the register. And this may be a little confusing, so let me bring the Word document back up and give you an example of a load word instruction along with it. So it's going to be load word S0, and we'll call it 8 S1. So this sign immediate that's the 16-bit value in the I-type instruction. The RS is the base pointer to the array, and this RT value, which in this case is S0, is where we're going to store it in the local register to perform an ALU operation on it. So if we have load word, and so the opcode is 23 hex, which I've indicated here. And so the immediate value, the actual binary representation, machine code language, is this. Now, store word instructions. So if I have a value load, let's see if you guys, so if load is, I'm grabbing something from data memory and putting it into a register, what do you think store word is? Saving it. Exactly. Taking it. That's a very simple and concise way of describing the definition. I like it. You're saving it. And more so because you have the registers are volatile SRAM. If the computer shuts down, you lose that data. Non-volatile memory, you're saving it by taking it value from the register, and then you have the second register, which is the base pointer in the array. You calculate the location in memory, and you save it to your data memory. So that's known as store. So let me scroll up here a little bit for those of you in the back. Store word instructions are instructions that take an address calculated by the ALU and stores the value from a register specified by the instruction to that address in memory. And so, let me separate this out. The opcode for store word instructions is 2B. So what is B in hex? Yes. So now we translate down here, 101011. And so store word and load word are both I-type instructions, and what this means is the memory value, the memory element at this location that's calculated by the ALU is going to equal the 32-bit value stored in that register. And to scroll up just a little bit to give you this instruction, the value at the register RT is going to be equal to the element in memory equivalent to the value calculated by the ALU. Okay, so if you have ever, for those of you who've coded in C and you're familiar with malloc and calloc, and you allocate, let's say you allocated 5 elements to your int array, and then you did this. So RS plus 7, so that would be the same thing as trying to get A of 7, right? But you only have 5 elements in your array. What does that cause? What's that known as? What's that? Array out of bounds. No, that's in Java, array out of bounds exception. What happens when you do that in C? How many of you actually coded in C? You coded in C++. How many of you coded in C? What happens when you do this? It starts with an S. Sometimes. Sometimes.
No, actually, I was going to say sometimes it's seg fault.
Yeah, sometimes it's going to seg fault. Okay. Ignore me for a second. There is something called a segmentation fault where you screw up the memory, and that's a possibility. Okay, so oh, C, what a language. Okay, so yep. Don't scare them, Lee. Okay, so anyway, so when you do store word, you're saving it to. That's my new favorite phrase, by the way. I like that. You're saving it to the data memory. So let's do this example problem 4.11. So we have A of 7, the 7th element of the array in A, plus C equals A of 8. So this is going to require a load word and a store word operation because you got to get something from memory, to store it from the registers, add it to a value in the registers, and then store it back into memory, right? But in a different location. So here's the thing. MIPS uses something called byte addressing. And the point of byte addressing is, and in section 5 we're going to get into more about the ideas of temporal and spatial locality. But the idea is, a byte is 8 bits, right? Yes? So MIPS stores data in 8-bit chunks, or known as blocks. That's the technical term for it. So you have 8-bit blocks. But how big is a MIPS instruction? 32. So how many blocks would you need in order to get one value? 4. So here's the thing. When you get let's say you have A of 3, right? And you're adding the offset. So you have the first bit that you're pointing to is the base pointer of the array. If you just add 3, you're going to go to the 3rd bit, correct? But that's not what you want. You want the 3rd 32-bit value, right? So what happens is all of these are pointing to 8-bit values, 8. So instead of getting the 32-bit values, you're only getting you're getting the incorrect data. So MIPS, by using something called byte addressing, you have to ensure when you actually translate it to the assembly language and then the binary, you take the value in here and multiply it by 4. So the value that's actually going to be physically in the load store operation, we have A of 7, right? So that's going to be equal to load word, and we'll call it temporary register T0. And the offset is going to be 7 times 4, which is what? 28. 28. So it's going to be comma 28, and which one is in? Which A? S5. And the reason why it's 28 is because so 0 through 3 is going to be element 0. 0 through 3, 4 through 7 is going to be element 1, because each of those are pointing to an 8-bit chunk, correct? That's byte addressing. So 28 means I'm getting elements 28, 29, 30, and 31, and then combining them into one 32-bit value. Why that is, let's press the I believe button right now. Section 5. But that's what happens. So, as I alluded to here, it's actually going to be S5 plus 7 times 4 is the actual memory location for A of 7. So, what's going to happen is we're going to load it into a temporary register, add C, which is S3, and then we're going to store it. So, if load word is this, where it's A of 7, so what is A of 8 going to be? So I have store word, which is SW. I'm going to take that value I added in T0, comma, and it's A of 8. So what's the value for the sign extended byte going to be? If this was 28 here, 32, exactly right. A times 4. And that is S5. Does that make sense? Great. I'm more than happy to explain it again. What time is it? Okay, we got time. So what's happening here?
So you're storing both of them into S5, or?
No. So I'll scroll this up and I'll show you what's going on here. So we take the value. This is the representative of A of 7, right? And then we're loading it into T0. The reason why I had the TGO where you write all this out is because a very common mistake on exams is people get the order of load word and store word confused. So I'm having you guys actually, this is what it is, this is what it is, in an attempt to save that's specifically to save you points on the exam. Right. So then from here, we have the value stored in T0, and we're going to add C. And the reason it's in this order is because it's A7 plus C. And then we can update T0, because since it's temporary, we don't need to save it in a register, right? So we don't need to save it in a saved register because it's just a value that we're performing an operation on and then storing it in the next one, right? So this is okay. This is acceptable. Once you no longer need the old version of this anymore, you can overwrite it in a temporary register. That's the beauty of temporary registers. And then storing is R of T of 0, so that's this one, is stored into 32 S5. Does that make sense?
Or what you stored into?
It's stored, okay, so this is the base pointer of array A, right?
Mm-hmm.
And the offset is 32. So that means we're going to be starting with the 32nd block. So 32, 33, 34, and 35, right? Those three 8-bit blocks are going to receive the 32-bit value coming from this register. So I don't want to get too much into section 6. I don't want to be drawing out data paths quite yet. But there's the registers, and there's going to be one register there's two outputs because we have two RS and RT. So on the other side, you have two 32-bit values coming out of the registers. And then one of those is going to go to the ALU to be added with the immediate. Recall when I was describing all the control signals, you have to have an ALU source to define the difference between if you're doing an R-type instruction and you're adding both registers, as opposed to adding the immediate value. You need to make a decision. And we use, if I have two 32-bit values that I'm trying to choose between, what logic structure would I use? I'm trying to have two 32-bit values I'm choosing, and I have one 32-bit value out. Which logic structure, which you did in assignment 1? Bingo. So you're going to be using those all over the place in the data path. Or in your case, of 16 to 8, because we're now at an 8-bit value. So here's where it starts getting a little weirder and simultaneously answers George's question from earlier. When would we use shift left logical? So if I have a value in a register, so here's this question here. We have a value of integer b, so we don't know what b is until runtime, right? So we can't deal with that with the compiler, right? We can't just calculate it as integer. Plus c equals a of d. So what I need to do is I need to take the value in that register, right? Now we represent it, the coder's going to represent it like if we did a of 7. What did you guys do? You multiplied it by 4 and then added the offset. Well, we don't know what this value is going to be. So we have to somehow multiply that by 4 and then create a pointer to the new location in memory. So, but if you recall from the arithmetic section, multiplication now, sign multiplication can require 2 to the n, 2n plus 1 cycles, right? That's right, you guys have already cried and put that out of your memory. So it requires 2n plus cycles because you have to have 2 to the n plus 1 bits, right? But let's say if I want to multiply by 4 in one cycle, or multiply by 2 in one cycle, or multiply by 8 in one cycle, or 16 in one cycle. How would I do that, George? Shift, left, logical. Exactly right. So if I have, let's say I have 3, right? And I want to turn this into 6. What do I do? Shift, yeah. So I multiply by shift 1, becomes 6. I want it to become 12. What do I do? From 3. I would shift 2, right? So if I had a of 3, this becomes 12, and the way we do that is shift left logical 2. So here's the thing. At runtime, there's no guarantee of what that value is going to be. So we have to take the value from the register, do a shift left logical, and then store it in a temporary register, right? Because we don't want to change the value of b.
Is that why they chose multiplying it by 4 to be the
Bingo. Makes life easy. Okay. And now, so now we have multiplying by shift left logical by 2. We can do it in one cycle. And as we discussed earlier, we do that with one-hot encoding. So it's fast. So you can do that in one cycle. So now you have the value in the temporary register. So that's now, the temporary register is now b times 4. So we've done this first instruction. We now have b times 4. So this b times 4 value, that represents what? If the value of a in S5 is the base of the array, right? The pointer to the base of the array, and I have b times 4, I've said it a couple of times today. What is this value? When I added 32, you remember what term I used for that? Of the base of the array plus the offset. Yeah, offset. Right? So here, this first calculation, we calculate the offset from the base pointer. So then, what I do is I take T0 and S5. S5 is the base pointer of the array. So it looks like this. Sorry for those of you watching this later on the video, but you have this block of memory, and you have the base pointer. So this is S5, right? S5 is pointing to this 8-bit chunk as its initial value, right? And now we've calculated b times 4 and added it, and now we're pointing to these 4 blocks, correct? So this is our offset here. And so the thing is, I don't want to compromise this pointer, right? If I were to change this, if I were to change S5 and I were to move this down, then I'm no longer pointing to the base. I've now changed the value of the base pointer of the array to A of B. So we don't want to do that, correct? So what do we want to do instead? If I don't want to change the saved register value, but I need to store it in a register, where would I save it? Temporary register. Hence why this instruction here, the second instruction, let me highlight it for those of you watching on the video later. So adding the temporary values, that's b times 4 plus s times 5. So now we've calculated the offset and storing it in a temporary register. Now I use the same one because we no longer need b times 4. If you did, but here's the thing, if you did T1 on an exam, sure. I'm not going to take off points. If it helps you keep track of it easier. If this is something that you feel is too complicated, that's fine.
Does it really matter as long as it's a temporary register?
As long as it's a temporary register. But the thing is, eventually you get run out of temporary registers. So I did it this way for condensing. But I will not give you any code on an exam that will require more than 8 temporary registers.
Use our temporary, then store something else in that.
Yeah. And sometimes you want to save them when we get to loops next class. We will show examples of when you do not want to overwrite them. So now I have the base pointer to the new elements, right? So if I'm pointing here now, I've created this T0 now, that's a pointer. That's a legit pointer. For those of you who want to know what pointers are, you just made one. This is an actual pointer right here. It's temporary register. So now that I have these 8 blocks, what would be my offset from this pointer that I want? No. If I'm pointing at what I want, how far would I want to go? If let's say you have 5 sandwiches, right? And I'm pointing at the sandwich that I want now. I want this sandwich. How many sandwiches would I have to move down to get to the sandwich I want? If I'm pointing at the sandwich I want, I'm already there. How many sandwiches do I need to move down? I'm pointing at the sandwich I want. So you just grab it, right? There's 0. So that's why this next instruction here is load word offset of 0. This pointer is now pointing to A of B. And then now that I no longer need A of B, I stored it in a temporary register that we're going to add. So here, using the register type instruction, this now contains A of B. And then we're going to add T of 0 and S of 3, store that into a new temporary register. Uh-oh, we don't know what D is. So now I have to go through the same process that we went through here. S4, multiply by 2, same thing as shift left logical. Add the offset of S5 to T1. This becomes the new T1. And then I store my saved temporary register into the pointer. This is now pointing to A of D right here. So let's, so we had 4.12, 4.11, 4.10, 4.9, and 4.8, correct? So 4.8 through 4.12, example questions. And the TG, we only did load word and store word, right? Yeah, 4.23 through 4.24. And next class, we're going to discuss loops. Homework 13 is example questions 4.8 through 4.12. Okay, does anybody have any questions before I dismiss you? Excellent. I'll see you on Thursday. Sure, what's up?
Right there we have, at the last, that line right there that you're on.
Yeah.
So we have our temporary one with has our AD, right?
Yes.
And so
It's
we're
pointing
at that.
Mm-hmm.
And then we're storing it to T0.
We're storing, this is the local register that we're performing the operations on, T0. We're storing T0 into the data memory.
Okay.
Does that make sense? So that represents, if you look at, I'll keep this up, so I'll explain it so the class can hear this too. So you have the MIPS screen sheet, right? Load word, store word, but so that's sign immediate, it's an I-type instruction. So you have RT, and if you remember from any coding, you take it from right equals left, so from the right, RT is equal to the memory, this M is memory, and then this is the pointer to it. Does that make sense? Okay. All right, good deal.